All right, I think we can start. It's that time. My name is Louise Edwards. I'm a program officer at the National Science Foundation. And before we start, I just want to say it's the NSF Simonyi Scholars Special Session. And I want to give a big thank you to Charles Simonyi, who, through his generosity, has provided the U.S. National Science Foundation section of astronomical sciences additional funds that we use to be able to support more early career researchers, fellows, career AAG, our regular astronomy grants winners. So we are able to support more science that goes towards learning about and understanding about Rubin. So I want to say that before we get started. Also, our regular reminders, there's the code of conduct. If you have any issues, please contact the folks on this slide. And respect folks' boundaries, both with their social batteries and their fist bumps or handshakes.
Hi, everyone. This is Burçin Mutlu Pakdil. I am your lovely chair today. And today we will be hopefully on time. So we have 12 minutes talks and including questions and answers. So after each talk, we will have one question during the exchange. And after that, we will wait to the end to see if we have enough time to have more questions. And Dartmouth grad student Sasha Campana will help with the mic. And with that, I will let Igor take it away.
Thank you. We should switch the slides. Thank you. Is this the pointer? Let me know when it's good to go. Thanks a lot. Hey, everyone. I'm Igor Andreoni from the University of North Carolina. And I would like to tell you about this project that we were fortunate enough to have support from Simone and NSF since a few years ago. And I think we're at a pretty mature stage of the project now. I would like to just bring some of the updates to you today. The overarching theme is enabling time domain and multi-messenger astronomy using not just Rubin alerts, but synergies with high energy telescopes as well as radio telescope, and try to really bring all that the new observatories can offer together. Who we are, it's a bunch of fairly young junior people, very excited about what's coming. In particular, Ashley Villar from Harvard, Eric Burns at Louisiana State University, and Michael Coughlin at the University of Minnesota. But from last year, I had to add a lot of people in the contributors list. We're very happy to have students joining the project, postdocs, and even staff scientists and researchers that just liked what we're doing. And we were very happy to welcome them in the crew. The overarching goals that we are seeking are how can we say more about big questions such as the production of heavy elements in the universe, how matter behaves within neutron stars, all the way to what cosmology we can do thanks to the study of merging compact objects. Those sources emit gravitational waves. When they merge, they can be detected by the LIGO and Virgo interferometers. And once that happens, what we would like to see is a global effort for the follow-up so that an electromagnetic counterpart to the gravitational wave signal can be found. And this is precious. I think we heard some of the talks this week about the power of bright sirens for cosmology. You can say more about the neutron star equation of state. And in my case, what's a bit closer to my heart is understanding better the astrophysics of the mergers and how the ejecta behave, and try to measure how much of the heavy element production has happened, how much nucleosynthesis has happened via our processes in the ejecta for these very rare and yet informative type of events. We're not stopping ourselves just to this type of mergers in terms of energetic explosions that we're studying. The study of gamma rebirths from collapsars, so from massive stars that undergo core collapse, is another one of the big pillars of our project. When massive stars run out of fuel, collapse, and if they're particularly massive or under certain condition, they can launch relativistic jets. What you see here is just an artist's representation, but as you can imagine, if you're lucky enough to be on the line of sight of the jet, then because of Doppler boosting, relativistic effects, the energy is increased by a lot. That's why you can find them in the gamma rays. And you can see these type of sources very far away, even to high redshift, redshift 6, redshift 8. And what we started doing is, let's start from what we've learned historically from the study of gamma rebirths with associated supernovae. If you find a supernova that is associated to a gamma rebirth, you can be pretty sure that what you're witnessing is the core collapse of a massive star. And what we did is, first of all, a comparison. What are we expecting from Rubin, and what are the limits that we expect to reach from Rubin, thanks to its observational capabilities, and therefore, what's the expectation in terms of rates? How many of these sources can we find, and how well can we study them? What you see in these plots are essentially light curves. So you always have magnitude on the y-axis, time on the x-axis. And typically what we're after are transients that evolve fairly rapidly at the beginning, in the first few days. I say fairly rapidly because Rubin is so deep in its observations that can observe gamma rebirth afterglows even up to a week after the burst happened, which is not typically what smaller class telescope can enable. After that, you may look for a thermal component. You may look for effect of nickel decay and the actual supernova. One work that I would like to advertise that is still in preparation, so stay tuned for when Anna finishes the paper and we manage to circulate it to the community, is really estimating rates and how well we can do parameter estimation for relativistic jets and supernova from collapsars, as well as for neutron star mergers. So mergers of compact objects with at least one neutron star component. This is kind of the hot topic because that's our primary target for gravitational wave follow-up. In this plot, this is a preliminary result that Anna obtained by simulating kilonova, which are fainter and faster than supernova. This is a trend that is associated with neutron star mergers. And here the kilonova is the thermal component in this plot marked in red. And you can see in this plot out to what distance you may be able to find this thermal component, in some cases associated with a non-thermal component brought by essentially the synchrotron from the afterglow itself. And I think it's nice to know we should be able to observe those with Rubin out to about 1 gigaparsec. I think actually we can go beyond that in some cases, depending on the properties of the transit itself. And if you want to limit yourself to the non-thermal component, once again, because of the beaming effect, you can see it much further away. And even the afterglows tend to be much more luminous, even if they're rapidly evolving, than most of the transients. And we can expect to see them out to 3 gigaparsec with Rubin. A big component of this project, like I mentioned before, is synergies. So we started studying prospects for synergies with other optical and radio telescopes, in particular, telescopes part of the new Schmidt Observatory system. Those include the Argus array, which is a facility that is made of 1,200 small telescopes working together. It's been built at the University of North Carolina, where I'm based. And it's very complementary to what Rubin is going to do. Rubin is all about wide field and depth. Argus takes the wide field to the limit, essentially, with 8,000 square degrees instantaneous field of view and very high cadence, up to 1 second in bright time. What you see in this plot is a simulated light curve of gamma ray burst afterglow as observed at the highest cadence with Argus. And in more normal times, when it's dark and gray time, the cadence will be 1 minute. And this is a more kind of typical view of what electron will look like. So Jim Freeburn, my postdoc, has just published a paper in which he estimated that Argus can find up to around 120 of such afterglows independently of any gamma ray burst detection from high energies per year. And what about Rubin? Rubin can find them for a long time, but still the cadence is just not great, at least as we have it now. The expectations are about 1/3, but corrected now lower than that because of the additional downtime engineering that has been forecasted. So let's please give another push to the Rubin cadence. So ultimately, what we want to do is take alerts, take information about transients from multiple observatories, put them together. I don't know what happened there. And essentially have a workflow that pull this information together in a way that can be promptly analyzed. And our final goal is to create some new type of alerts that are comprehensive of alerts from Rubin and other facilities with information on parameter estimation that can flag neutron star merger counterparts and relativistic transients or special type of supernova in near real time publicly to the whole community. And I will stop there. Thank you.
While Dimitri comes, let's have a quick question, if there's any. From Alex.
Thanks for the talk. I was super interested to see the high cadence from Argus Array. Could you say a little bit more technically? Are you using CMOS? What's the technology that's
it's a science CMOS detector. So there will be one of such detectors per telescope. So 1,216 that work in parallel and together. And the readout time is like 200 microseconds. So it's essentially negligible. This is what enables this very high cadence and close to zero downtime, but for when the subarrays of the large array have to reset. So you can expect to have very regular observation throughout the night continuously, at least for, I think, for 5 years, I think is the nominal duration of the project. And it will be also, allow me to say, also complementary to Rubin because it will be located in the Northern Hemisphere. But like Rubin, all the data will be public.
Igor?
Thank you.
This one doesn't work for me, right? Oh, it does work. Great. Hello, everyone. My name is Dmitry. I'm from University of Washington, and I'm really happy to present our project here, which is called Rubin Rocks, a statistical analysis of near-Earth objects' dynamical histories. We're doing it with Sarah Greenstreet and Siegfried Egel as supervisors, and me, postdoc, and Sam Cornwall, graduate student. We're really thankful the Simonyi Foundation for the support for this project. So what are near-Earth asteroids or near-Earth objects? These are asteroids and comets which are coming near the Earth. So technically, the definition is that the closest distance on the orbit with the Sun is less than 1.3 astronomical units. And they are in general divided by 4 classes. So one is the Amur asteroids, which are coming close to the Earth, but still mostly outside from the orbit. The Apollo class, which is crossing the orbit, but still like traveling outside of the Earth's orbit. The A10 class, which is also crossing the orbit of the Earth, but now they're traveling mostly inside the orbit. And the Atira class, which are completely inside the orbit of the Earth. And as you can see, we did not discover lots of Atira class asteroids. It's only 38 of them right now. Yes, we don't expect a lot of them to be, but still should be about 1% the whole population. And yeah, but they're more difficult to find. There's also a subclass of Atira class asteroids, which are the ones which are traveling inside the orbit of Venus. So they're even closer to the Sun. And right now there's only one asteroid which is discovered like this, and the whole subclass is named after this asteroid. And I'm sorry, I cannot pronounce it. The one problem that we have with near-Earth asteroids is they cannot survive on the orbits for long. So in general, for 10, 100 million years, something happens to them. They either ejected from the solar system, or they hit the Sun, hit some planets, so something. But our solar system exists for more than 4 billion years, and we still see the near-Earth objects. So that actually means that there's a constant source of these objects, something pushing them. And yet, yes, so they are originated mostly from the main belt, in different regions of the main belt, which are associated with resonances with Jupiter and Saturn, sometimes something else. But since they're coming from the main belt, from some regions, that actually means that they're the probes of that parts of the regions of the main belt. And that's the motivation for our project, Rubin Rocks, because since these objects, the near-Earth objects, are the probes of that part of the near-Earth region, that means that if you study them, study the near-Earth objects, it's kind of like you're studying that part of the main belt. So, but for this one, you need to know where they actually came from what part. And this information becomes really, really valuable. And so in our project, we provide 2 complementary approaches to solve for that. So the first approach is the fast statistical approach. So you can just query the pre-computed statistics of the dynamics of these objects via web service of API. Or we also provide a numerical integrator, so you can just put it and integrate yourself. Of course, you'll have to probably wait for days for that instead of seconds for the statistical approach. But if you have a more unique object, which is not typical one, let's say, then probably the statistics is not going to be good enough. About the web service. So it works as a website. So you just go there, put the orbital elements of your beloved asteroid, and it gives you some of the information, which is probably the most important one, the probabilities that it came from different regions of the main belt, and some other information. I probably don't want to talk a lot about that. In the future, we want to add even more, which I think maybe the most interesting here would be the end state. So like, what are the highest chances what's going to happen with this asteroid after? So maybe it has higher chances of hitting the Earth, or maybe even Jupiter, or maybe being ejected from the solar system. And that actually works pretty great if you have one asteroid, your favorite one, maybe 2. But if you have thousands of them, probably it's not a good idea to all the time going to the website and putting the whole list information yourself. So you can use an API. And with this one, yes, actually you can scan the QR code. So that's going to give you the documentation of this API. There's a Python code as well. Thank you. retrieved. And so imagine you're an observer and you have a list of 100 objects that you can observe this night, and you want to know which one you would like to observe. And so, for example, you can go to our API, see from what regions of the main belt they came from, what are the chances that they came from this region, because sometimes there are going to be really high chances that it came from this region, and it's much better than if you have the information of 50-50. And then, yes, you can study specifically that object that you're interested in. So that's a way how to stack that. Right now, several days ago, I got the update that right now you don't even have to put the orbital elements of them. You can just put the asteroid designation, and our API will automatically query the NASA small body database, get the orbit, covariance measures, everything, and just give you the information. The second approach is the numerical integrator. And it's not even a symplectic integrator, which in general people use for long-term studying dynamics. But we modify that to preserve the accuracy. So I'm not going to talk a lot about how good this is. I'm just going to say that it has an adaptive time step. So whenever, let's say, an asteroid coming close to a planet, the integrator is going to reduce the time step itself. So taking this into account. And there's also no restrictions to the forces that you implement in there. So it's not only orbital dynamics, but you can put even relativistic corrections, or maybe you're studying comets, which has outgassing. You can put these forces as well with no problems. We did test this integrator a lot, and I'm going to present only these two tests because otherwise it would be really long and boring. We compare it with the two quite famous integrators as WH-FAST and IS-15. And these are the two tests. So imagine you have the solar system, so all these 8 planets, and then you add a set of 50 asteroids, and then integrate for 1 million years. And then you can exchange these 50 asteroids to another set of 50 asteroids, and also integrate for 1 million years, and so on. And let's say we do this 25 runs. So the first thing we can check is that the total energy of the system, because it's a closed system, well, so the total energy must be conserved. So we can check how conserved it is. And this is what you see on that plot. So yes, you see that our integrator lobby is these blue dots. They have the lowest one, so that means this is the most precise, and also quite good in terms of the performance. But look at the right plot. So this one shows how consistent the orbits of the planets are, because ideally, the planets, they don't fill the asteroids. The asteroids have 0 masses. So ideally, between these 25 fronts, the planets should go exactly on the same paths. But it's numerical integration, so they still diverge. And this divergence can tell us how accurate our integrations are. And look at Jupiter. So there. So after 1 million years of integration, the consistency of Jupiter is 1.5 kilometers. And when I actually saw that, I thought there's some problem with the checking probably a couple of orders magnitude or something. Maybe I forgot about the kilo something, so it must be maybe kilometers. No, it's actually 1 kilometer. And this is what we would like to use this integrator for, to study that parts, that subclass of near Earth objects, which I could not pronounce, how they actually become them, what's happening with them on their path. And I think this is it. Thank you for your attention.
Well, Danielle is sharing her slides. We can have a question for Dimitri. If there is any. Okay. Let's thank Dimitri. Thank you so much.
Hello, everyone. Can you hear me?
Yes, we can.
Great. Okay. Thanks. Apologies, I couldn't be there in person. I'm going to include my email at the end, and then I'm also on the Slack. So if you guys have any more questions, just let me know. I'm Danielle Frostig. I'm a Simonyi NSF postdoctoral fellow. I'm also PI of Boombox. I'm excited to tell you guys about the new spectrograph we're building today. So Boombox, just to have a summary up front, is a pair of multi-object spectrographs for the MMT and Magellan 6.5-meter telescopes. It has 36 robotically positioned fibers going into a dedicated low-resolution R1000 spectrograph covering a broad wavelength range from 360 to 1010 nanometers, doing about 100,000 object survey over its lifetime. We're working hard in the lab now to get it all built, and we're hoping to be on Sky next year. So in light of the beautiful data we've been talking about in this workshop, there's a lot of opportunities coming, but it also gives us a couple of problems to contend with. First is that we need more spectra. I'm a time domain astronomer myself, so my examples are going to skew in the time domain, but this is true of basically any field of observational astronomy. If we look at the number of supernovae we've been discovering for the last few decades, we can compare how many we discover photometrically to how many we can follow up with spectroscopy. And right now we're hitting about 1 to 10% of everything gets spectroscopic follow-up. But as we know, Rubin's expected to discover about 1 million supernovae per year, and our spectroscopic resources are not scaling up to match, leaving us with less than 1% of everything followed up spectroscopically. The other thing, Igor talked a little bit about the multi-messenger case, is we often need these spectra quite quickly. In this example, if you look at neutron star mergers that we have gravitational wave signals for, and we can follow up photometrically, we then want spectra, but the spectra evolve quite quickly. So I'm showing here an example of the spectra from GW 170817, just to show that even 12 hours after the event, when we first got on Sky, the spectra evolved quite quickly, and we think maybe even in those 12 hours, we missed key signatures of heavy element formation. We also often want to do the spectroscopic follow-up on large telescopes. So where I work at the CFA, we have two main resources we use. We have the 6.5-meter MMT observatory and the Magellan telescopes. But these telescopes are quite popular and can be hard to get time on. So we have to get really creative. It's hard to do single object spectroscopy for such a gap of spectra. So we think creatively about the new instruments coming online and how we can use that time. So that leads me to the VIA survey, which is a large-scale survey operating over 150 nights per year, over 5 years, getting 3 million spectra. And the VIA survey has very specific science goals, which don't help me as much as a time domain astronomer. They're looking at things like stellar streams and dwarf galaxies and looking for signatures of dark matter. But when they point at all these different places in the sky, we're in this era in which any given place you point with a 6.5-meter telescope with a 1-degree field of view, there should be at least one bright active transient we can characterize. So we can really capitalize on this time. That leads me to Boombox, which is named just because it's a box to study things that go boom. And I'm introducing a few different names here, so let me break it down. Overall, we have the VIA project itself, which goes on these two different telescopes, MMT and Magellan Clay, doing a large-scale survey with a 1-degree field of view. It breaks off into these two different spectrographs. We have VIA Spec, which is the main spectrograph, and for my scientific purposes, it covers a relatively narrow wavelength range, 505 to 595 nanometers. It's pretty hard to classify transients with that, but they're really prioritizing a high resolution, high stability spectrograph to do radial velocity studies. On the other hand, we can add Boombox, add a second smaller spectrograph that covers a broad wavelength range, so 360 to 1010 nanometers, at a lower resolution, but really prioritizing a high instrument throughput, getting as much light as possible so that we have a depth limit of about 23.5, which I'll talk about more later. So that's the concept behind adding Boombox. So I'm going to give you guys a very, very quick tour of the instrument itself. So light comes in from the telescope and it gets focused at this fiber positioner. The fiber positioner holds over 600 fibers going into the different spectrographs and into different calibration systems. You can see in this video, hopefully it's coming through on Zoom, that we have 6 of those fibers in the test stand on their dedicated robot. So we have these robotic fiber positioners that patrol around in this circular radius, which helps them grab any targets of interest. So if you look at the whole focal plane, what you can see is that we have most of the fibers going to via spec, and those are all the ones in white. And then the boombox fibers are the ones in white with a magenta circle, and the circle represents that patrol radius. So anywhere a boombox fiber can grab a target. And anytime we point the telescope for a via spec observation, what we can do is decenter and rotate the field so that we can grab any of these targets of interest. So that's why we've picked that spoke design that you can see throughout the field. We also can interrupt, which I'll talk about later, and grab targets we care about ourselves. So this leads me to our 2 observing modes to solve those 2 problems. The first problem was we don't have enough spectroscopy. So that leads me to this spare fiber observing. So these 500 nights that via spec is on per year, Boombox's dedicated low resolution fibers will be doing a background survey of grabbing these targets of interest and characterizing them. And we've done many simulations of Rubin transients that we expect to see and how many we can get on our fibers. So we can, as I said, decenter and rotate. And depending on the density, at the lowest densities, we can really still get about 3 targets. And as we get higher, we get about 30 per pointing. In addition, we get 10% of the overall survey time to do target of opportunity interrupts. So very quickly say, we're already on the sky, we're already observing, but let's go over there. We think there's something interesting happening and grab that target. So that gets us about 10 nights a year on 6.5-meter telescopes. So you can do a lot of science with low resolution spectroscopy on large telescopes. I talked about supernova and kilonovae. We're doing lots of other kinds of transients. We heard about comets in the last talk. We're also interested in comets. We're interested in persistent targets, so things that don't change over time. And these boxes are actually all pitches submitted by different members of the collaboration. As you might be able to tell, this is a relatively young group, so a lot of these are student and postdoc projects, which I'm pretty excited about. Okay, so continuing our tour of Boombox, we go from the fiber positioner, and then light goes in through the fiber chain into the 2 different spectrographs. We're going to zoom in on Boombox and talk about it very quickly. Light comes in from the fiber slit. I'm showing the optical design here. Gets collimated and split into 2 different channels, a blue and a red channel. And this was important to really maintain high throughput. This lets us pick special glasses, special coatings, and special gratings to make sure that we get as much light as possible through the broad optical range. I'm showing here our mechanical design. It's almost fully complete. We also have our detectors already in-house. We have our gratings, which are binary diffraction gratings in the lab. Some of our optics, the rest are coming later this year. We're finishing up some of the last mechanical details, and we'll start manufacturing the mechanics very soon. And I'm excited that it's all coming together. So if you put together our optics, our mechanics, and our coatings, and all the things on the telescope, the fibers, you can look at the throughput, or how much light gets from the sky in through to our detectors. And you can see with everything included, we have through the blue and the red, over 30% throughput for many of these optical and nearest infrared wavelengths, which will help us characterize things that we don't know what they are yet. We don't know what redshift they'll be at. So we have this broad information space. If you put this all together, we can simulate our signal to noise ratio and what we might see. So if we look at our depth, we go down in the dark time at 0.7 arcsecond seeing, we can get to about 23.5 magnitudes in an hour. If you look at simulated spectra that we've made based on our simulator, we have an image simulator for the spectrograph. You can see that at this low resolution, at sort of our seeing limit, that our spectra look a little bit noisy, but very distinguishable. So this is, I'm plotting the flux of a kilonova simulation versus 2 different types of supernovae at this low resolution. And you can see, while it's noisy, you can very easily distinguish between the different types, which is often what we're trying to do when classifying transients. And we can do that successfully in these simulations up to about 24th magnitude. If you put that in context of what Rubin LSST should discover, we can look at, based on the magnitude, of course, as you go deeper, there will be more fraction of these transients. Many other multi-object spectrographs are going on 4-meter telescopes, which get you about a 22.5 magnitude limit. This gets you about 28% of all Rubin transients could be observed with those 4-meter telescopes. When you go up to 6.5-meter telescope, like we're doing with Boombox, we can get about 70% of those transients just based on depth in about an hour. So we're excited to go after some of those fainter targets. And then, of course, for anything even fainter, you need more time or a larger telescope. So as a quick summary of what I started with, Boombox is a pair of multi-optic spectrographs for the MMT Magellan telescopes. It's got a relatively low resolution and broad wavelength range to do many different surveys, and we're hoping to grab about 100,000 objects, and we plan to be on Sky next year. Thank you all for listening and listening on my Zoom presentation.
Thank you so much. Any questions about Boombox?
Hi, this looks like a great project and it looks like a very experimental one. I was wondering, have you guys investigated the size of these optical fibers and the material of these optical fibers? Like, have you investigated with other, because I used to work on like titanium dioxide waveguides and stuff, and I know the size of these waveguides and the material you're using can play a very big role in these.
Yeah, that's a great question. They're fused silica. The size on Sky is about 1.2 arc seconds. It's definitely something we discussed extensively, especially because with the two different telescopes where we have different seeing at both sites. So we talked about having larger fibers potentially at the MMT or for different science cases. We ended up going with these fibers just because it was operationally easier to have so we just matched the same fiber size as via spec, just because it's so much easier when we're putting everything together and putting it on the robots. But that is maybe there's a few trade-offs we've made to be in the same focal plane as another instrument. Is we went with their optimization, but we think it will work well for most science cases.
Let's have it.
Hi, this is Shreya Anand. Great talk. Thanks for the talk. I was wondering if you have an estimate of the number of supernovae you might, or the number of transients you might be able to observe in a given night with Boombox. I don't know. Sorry if I missed this.
Oh yeah, no, great question. In a given night, we're doing, if we're a passenger, so if via spec is driving, we're doing about I think we're getting 2 or 3 transients from Rubin specifically, depending on the density in the field. Sometimes it's just 1, sometimes it's more. And then when we're interrupting as target of opportunity, we'll just prioritize usually putting 1 on our best fiber. So when I say 2 or 3, I meant 2 or 3 per effective hour, which is approximately where we're going. When via spec is running, sorry, there's many if this then that's. And then when we're running the survey, when we have that 10% of the time, we get to set the exposure time. So often we don't need as much time as an hour, and then we can get a few more in that night. I'm not sure if that answered your question.
Yes, it does. Thank you.
Okay.
I also had another quick question, which is, what is your plan for communicating findings to the community?
Oh, great question. Yeah, we definitely, that's part of the purpose, especially with this background survey, is to just let everyone know what the classifications are. So putting them on TNS immediately. We have a nice pipeline we're already working on to be analyzing things that night. And then with the specific student and postdoc projects, it sort of depends on the project. But definitely for the transient background survey or the other background surveys, the goal is just to get it out to the community so other people can also follow these things up, or know if they don't want to follow something up. Yeah.
Danielle?
Thank you.
And Mansi, take it away.
Great. Can you hear me okay? Yes. Hopefully. Can
Yes,
you
you
hear
can.
me?
We can.
Okay, perfect. Good morning, everyone. I just wanted to start with a big thank you to Charles Simonyi and the National Science Foundation for funding this work. So I'll give an update on the Baba Mole project, which is one of the 7 alert brokers for Rubin. Our team for this particular event broker project is primarily at Caltech, University of Minnesota, and UC Berkeley is providing the Sky Portal interface for the front end. Yesterday, Sushant Chaudhary and Antoine Lakolik presented details about the Babamol event broker at Eric Baum's session. So hopefully some of you went to that and got a good update. So I'll try to make this more complimentary and focus a little less on the software infrastructure and a little more on the science results. And then we have some special contributions from Northwestern and Montclair as well that I will highlight at the end of this presentation. So a quick recap on Boom's architecture. So Boom is the central backend to the software infrastructure we are developing for this event broker called Babamo. And there are several differences from your canonical backend for processing alerts. In particular, you'll see that we use MongoDB, so no SQL. We use Valkey for in-memory storage. We Rust, not Python. And if you look up our paper, you will see much more in detail, but we get a factor of 7 improvement over the Zwicky transient facility core backend that we were using that was called Kowalski. So this sort of prepared us for an era in which we get a much higher throughput of alerts from Rubin. And actually, as of this morning, we have some progress on some GPU testing that can give us another factor of 10 on this architectural design for the core backend. So Boom seamlessly merges the ZTF and Rubin alert streams for us, and our front end is the Babamol event broker. And more than this diagram, I just encourage all of you to just go to babamol.caltech.edu. About 463 people, the last time I checked, have already gone to this website, made accounts, and are using it. There's many ways in which you can use this. You can just go to the dashboard and see, oh, what happened last night with Rubin and ZTF, or you can use an API or your Python notebooks or Kafka to play with the alerts as best for you scientifically. Details are also linked on the top right to our paper. Now I'd like to dive into the science that is possible. We only have a trickle of alerts so far from Rubin. We are eagerly waiting for the fire hose, but even so, we can do some science. On February 6th of 2026, right at the beginning of the first alerts from Rubin, this Wiki Transient facility focused its public survey on this 10,000 square degree green overlap region that's accessible from Palomar, but at a 9 times faster cadence than Rubin. So we do G-band, R-band, and I-band every night for the same overlapping footprint. And our central motivation or core question really is, what science can ZTF plus Rubin discover alone together that neither survey can discover on its own? So with that motivation, right from the first day and the first alerts, we could take alerts from ZTF plus Rubin with joint detections, and we go get spectra with the next generation Palomar spectrograph on Rubin. And as Danielle was just highlighting, this increased throughput that is now possible for spectrographs mean that even with a 5-meter telescope, in 15 minutes, we can get very, very nice signal to noise, classifiable transients. And that's only with 15 minutes. Just to put this in context, now that we've been running for several months, we now have a spectroscopic database that is of 541 spectra with the NGPS spectrograph on the 200-inch. And these are all transients that are in the ZTF and Rubin footprint. Rubin doesn't have its full fire hose ready, so they don't all have Rubin detections, but hopefully soon that will be fixed as Rubin gets more reference images, and now that the LSST survey has begun in earnest. You can see what the breakdown of transients we are discovering and classifying in this overlapping footprint is. And we hope this establishes spectroscopic ground truth for all future machine learning algorithms that want to do this without spectroscopy, right? So, but you need a ground truth. So some of you would be excited about the big red pie, which is 2/3, which is type 1a supernovae. Some of you might be interested in this little gray slice of 4% in the other category, which are all kinds of exotic transients from superluminous supernovae to tidal disruption flares, even to fast blue optical transients as of yesterday. So really fun stuff. And if you only care about your backyard, you don't want to go too far out, then in the local volume, there's about 105 transients. So here's an example of a transient, a light curve, a spectrum, and then the corresponding classification as a nice type 2 core collapse supernova. Let me give you a couple of science highlights. So here is in March, we had Einstein probe detected the shock breakout of a type 1c broadline supernova. It was really quite spectacular to see the first X-ray photons. For this event, you see the joint ZTF and Rubin light curve here. ZTF is in circles, Rubin is in squares. And you can see, the photometry is very consistent. You can get good sort of joint data on it. And the U-band for this event was really unique from Rubin. There's very nice U-band photometry. There was some excitement for this event where Rubin saw precursor potentially, but without the prompt products yet. Those were hard to decide whether that was subtraction artifacts or a real major scientific discovery. So I think the jury is still out on that one until prompt products get released. Another example, and this is now a very canonical run-of-the-mill type 1a supernova. And you can here again see the joint ZTF and Rubin light curve, a nice spectrum. In case you had any doubts, this was a 1A. But what's beautiful is that Rubin can really sample that early rise, sort of between 23rd and 22nd mag, and that really late time data. Right? Is it actually following the nickel tail, which in this case it is, or doing something more spectacular at late time? So the very early and the very late is really beautiful how Rubin can already sample it even with its trickle of alerts. So this joint analysis has led to, I'm giving you a couple of examples here, but it's led to many astronauts. The postdoc Wynne Jacobson Galanis focused on a precursor watch, right? I mean, looking for detections from Rubin before the supernova itself. Postdoc Kostav Das is focused on late time detections, right? I mean, he's looking at transients that happened many years ago, and now they have somehow being detected again in Rubin, even though you don't expect to see them at late time. And that could tell you something about what happened to the star before explosion, because it's now running into that material. So there's all kinds of fun projects this can enable. Those of you who like high redshift things, there was some fun. About 3 now superluminous supernovae discovered around redshift 1 with Rubin. That is also possible with the Bapamol event broker here. Now, in the last couple of minutes here before I take questions, I wanted to highlight some work by our Montclair State University partners, Shaun Ghosh and students, where one of the challenges, software challenges that we have in multi-messenger astrophysics is we don't have a lot of information at the time of the low latency gravitational wave trigger to optimize the follow-up that is done with ZTF or Rubin or any of the large number of telescopes that are trying to look for an associated electromagnetic counterpart. So you can see the simple approach gives very poor accuracy of a very wide range, especially on a very key parameter, which is the inclination angle. So Shaun and students have been working hard on a neural network-based source classification that can try to improve upon this low latency estimate of inclination. And there is some recent progress that a student is working on a paper to try to just help optimize the follow-up that is done for multi-messenger observations, which you heard a lot about from Igor this morning as well. So this is one ingredient that can help optimize those observations that you heard about from Igor. I'd say another sort of key element of this program has been student internships. In the last year, we've had about 5 students go from University A to University B and spend about a month or so on average. And this has really helped put progress on projects in top gear, right? Because it's much more effective than Zoom to really have an opportunity for students to go and spend time at another university and work through projects collaboratively. So that has very much accelerated progress. And I'll leave this list of students up here, and I'm happy to take a few questions.
Any questions? I think we are good. Thank you so much. Again,
Okay.
Mansi. Yep.
Yeah, do you think it'll work? Okay. Hey everyone, my name is Ashay Pai. I'm a second year graduate student at the University of Chicago. And today I'll be talking to you about some work I did on studying the Milky Way satellite Virgo 3 with Rubin DP2 data. So let me give you a little bit of a background on ultra-faint dwarf galaxies. So these are galaxies that occupy the faintest, oldest, and most metal-poor population of the galaxies that we know. And they reside in the smallest dark matter halos, we think, that are capable of galaxy formation. Here in the image, you can see a few dwarf galaxies that are satellites around the Milky Way, from the LMC being the most massive at 10 to the 9 solar masses to some of the least massive in the bottom row. Now, UFDs are an extremely powerful cosmological probe for a variety of different things, and can be used to constrain galaxy formation, sort of understand the origin of heavy elements. They can be used to study reionization and also the nature of dark matter. So the plot here is the observed UV luminosity function at redshift 7, plotted and overplotted are masses of Milky Way satellite galaxies at this redshift. And you can see that apart from the LMC, all of the fainter and smaller satellites are sort of undetectable by telescopes such as JWST and HST. And so studying these galaxies around the Milky Way is a great proxy to understanding what was going on at these distances. So the current census of Milky Way satellites is the following. There's sort of two main types of objects, globular clusters and dwarf galaxies. The globular clusters sort of are the blue crosses shown there. And recently, so up until now, there was sort of separation between these two populations, but as of recent, with better imaging and better quality data, these two populations have started to merge. And we're seeing a lot of these, what are now called ultra-faint compact satellites down here. One of the key differences between the two populations is that dwarf galaxies are dark matter dominated and globular clusters are not. So what is the expectation with LSST? So here's the predicted luminosity function for LSST. And you can see that we've covered the relatively brighter end well, but most of these discoveries in the future will happen in this faint, ultra-faint, compact satellite regime. We expect to find these satellites out to higher distances, and we expect to see that these satellites are smaller and fainter than the ones we know so far. In total, we expect about 80 satellites to be visible in the LSST Wide Field Deep Survey. So what does Virgo 3 look like in DP2? So a little bit of information about the DP2 data. So Virgo 3 resides in the M49 first look field.
No, thank you. Nice. We are going.
A caveat here is that this field is much deeper than the rest of DP2 and sort of approaches the 10-year expected magnitude depth that we will find with LSST. So it's shallowest in the U band at about 25 magnitudes and deepest in G at about 26.5. So Virgo 3 was discovered 2 years ago in HSC data. And the way it was done was fitting an isochrone of an old metal-poor stellar population. And it was fit to a magnitude of about -3 and a distance of 150 kiloparsec away from us. And here's what the region in HSC data looks like, along with the fitted CMD and the member stars. So the HSC detection found about 25 stars. And here is the new DP2 data. So DP2 is a magnitude and a half deeper than the discovery data. And we recover up to 4 times as many member stars. So we recover up to 100 member stars belonging to Virgo 3, allowing us to look at the main sequence turnoff and slightly below it too. Now, a little aside on star-galaxy separation. So DP2 provides several star-galaxy classifiers, and a good star-galaxy separation is crucial to detecting such systems as the galaxies sort of reduce the detection efficiency. So this is a good way to validate the performance of these star-galaxy classifiers. We find that when we perform a likelihood analysis of this overdensity of stars belonging to Virgo 3, we find that our likelihood analysis prefers completeness over purity. So in other studies, ref extendedness, which is the black line there, is sort of the most permissive cut. It allows for the most galaxy contamination. And we recover a higher likelihood of finding Virgo 3 with that classifier. So a few other things we can do with DP2 data. So as these systems are metal poor, you can use precise photometry to separate out these in color space from the rest of the stellar locus and identify members. So we found that DP2 photometry is already good enough to separate out member stars that we found through the isochrone selection of Virgo 3 with around a 20 millimag offset from like the median of the stellar locus in the background. Another thing we discovered was, and this is currently not well studied, but since these data go deeper, so here on the left-hand side is the stellar overdensity corresponding to Virgo 3. And if you look closely below the main sort of core in the center, you can see hints of an extended feature from Virgo 3. You can also take, so what I did was I took vertical slices in RA and plotted them. And you can see that along with the main overdensity, there's sort of a central smaller peak. Now, this was not visible in the HSC data because when you looked at the stars in this region, these stars happen to be fainter than the magnitude limit of HSC. But obviously more work is to be done, and this can help or constrain tidal disruption to far distances from the Milky Way. And we would need spectroscopy to further confirm this. Another thing that was discovered in Virgo 3 was the presence of 3 RR Lyrae candidates, or RR Lyraes, in 2 years ago. Out of these, 2 were RRABs, or fundamental mode RR Lyrae, and 1 was RRC, or the first overtone. Since these data are nominally at the LSST 10-year point, there's enough epochs to perform variability analyses on this data. And so what we do is we fit distances to these RR Lyrae with theoretical period luminosity metallicity relations, along with performing template fits with templates from DES that are modified from LSST. We find that we recover the periods of the RRABs, and we find that the PLZ relation, however, sort of gives consistent results with the independent RR Lyrae distance measurements, but not with the isochrone. To conclude, a sort of prospect about the future of what we can expect with LSST. So in this data, Virgo 3 is an extremely prominent detection. It's about a 15 sigma detection. And here, the plot here is a prediction of the detection efficiency of ultra-faint dwarfs at the LSST 5-year mark. And the x-axis is luminosity with brighter objects to the left and size on the y. And this prediction is for objects that lie to far distances, so about 150 to 250 kiloparsec. And we find that Virgo 3 lies along what is here the LSST corrected expectation. And here the red contour that marks LSST corrected is the 50% detection efficiency. So LSST data currently are, or at least at the 10-year mark, will be match expectations from simulations that have been happening in the last few years. So this is a really exciting time for ultra-faint dwarf galaxies around the Milky Way, and we hope to find the AT that we predict. Thank you so much.
Any questions?
Thank you. The excitement builds. This is great stuff. I'm wondering, DP2 is a great data set, but it's not representative of LSST performance generally. And so a plot like this, we might expect to do better.
So this, yes. This is, I think, the 5-year expectation for the wide fast deep region of LSST. And yeah, I think depending on star galaxy separation and how well we can perform on that, there's certainly more we can do.
Any other question? If not, Gautam, please take it away.
Okay. Hopefully you can hear me. I realize I am the thing keeping you from lunch. So I will try to speed through this as quickly as I can, also because I need to make my flight. I was one of the first class of NSF Simonyi Career Fellows. And even when we had applied for this a few years ago, I was very concerned about dark energy and interested in combining Rubin data that we are now finally starting to get with the surveys. And the key question for me was, is dark energy actually a cosmological constant or not? You've heard this multiple times over this meeting at RCW, and supernovae remain one of our key probes to answering that question. Now, if you look at the distribution of supernovae we have, Where LSST is going to give you a whole bunch of supernovae very quickly is at that high redshift regime, replacing out most of those blue supernovae pretty fast. The challenge, though, is the low Z sample. We only have around 200 of them right now. And if you increase the number of LSST supernovae by like a factor of 10, you've got a really heavy lever arm on one side without something corresponding at the lower redshift end where dark energy actually needs to be pinned down. You need an anchor sample. And the low redshift end is where the sensitivity is, of course. We can see that despite using the same low redshift samples of supernovae, groups like Pantheon Plus and Union 3 with just different analysis techniques end up getting slightly different results. But irrespective, the key thing for me from these plots from DESI or from DES in the last couple of years has been that whatever we can do to get rid of systematics, there's still this like roughly 3 sigma tension with lambda CDM. And so the real question for me is this real or not, right? And to answer that question, you have to see what the big dominant systematic is for the low redshift sample. And it turns out to be supernova astrophysics. So there's a whole bunch of careful work that DES folks, Brody Popovich and others have done. And part of this is understandable. We just don't get very many low redshift supernovae at all. So for example, if you are looking for supernovae in Cepheid host galaxies, you have to use data from like the 1970s that were taken with photomultiplier tubes. I got news for you. You can't really calibrate that stuff anymore. It's pretty hard. But there's also just a whole bunch of new techniques that we should be trying to apply to our data. We don't really use very much other than the supernova light curve to this day, despite the fact that we get spectra, that we get host galaxy information. And so I wanted to think about a survey that we could actually use to different facilities and build a replacement low redshift sample. This became the basis of my career proposal. And with a bunch of colleagues, we call this the Young Supernova Experiment. We've been using the Blanco telescope in Chile with DECCAM, which was also where I did my thesis work, so it's always fun. And PanSTARRS, which is in Hawaii. We have roughly about 15% of the time on PanSTARRS 1 and 2, cover about 1500 square degrees there, about 300 square degrees with DECCAM. And with just these individual telescopes, we have roughly a 3-day cadence. We've been running this since about 2019, and we are funded currently through 2028, so we should have good overlap with Rubin. There's a whole bunch of colleagues involved, and compared to DESC, where there's like 1,400 people, this is like, a small Zoom room, which is really fun. Most of these folks have maybe 1 or 2 students involved in the project too, which is really great. We put out our first data release a few years ago. Patrick Aleo, who's now making the big bucks in industry, put out a sample of about 2,000 photometrically classified supernovae. This was the largest GRIZ sample at the time. And now Tana Murphy has been analyzing more data. And what more data gets you is more fields, more supernovae. So over 6,000 right now with PanSTARRS 1 and 2. But then the best part of this is once you start adding DECCAM, you can start moving further and further south. Right now, because Rubin's only turning on, we're still focused on the equatorial regions, but we'll be moving further and further south, of course, as Rubin's turning on. Tana's actually been working with a whole bunch of undergrads to do all of the data processing for this. So all of this has been student driven. What having multiple sites gets you is actually not just better sampling on the light curve, but better cadence. So since PanSTARRS and Chile are at different locations on the Earth, and we can also combine our data right now with ZTF that Mansi talked about, we can get sub-day cadence. We can frequently get 3-hour differences in observations, which is simply amazing. And if you are sticking around here for Rubin 2036, I would love folks to make that point, that having more telescopes in more locations is always good for time domain. Hi, Ed. So what do we have for DR2 right now? About 6,000 some odd supernovae. These numbers will probably change a little bit, but actually only in the upwards direction. And that's because we focused on our detections where we have both PanSTARRS and DECCAM. But there are a few things that we're trying to get out of the DECCAM data that are not in PanSTARRS, that do faint for PanSTARRS. But this was only till 2024 to date. As of at least a couple of weeks ago, we have almost 13,000 of them, which is really, really impressive. And that'll be in data release 3. about 4,000 odd, 4,500 odd have a spectroscopic redshift, mostly from the host galaxies, but about 1,000 of them have a transient redshift. And so median redshift of about 0.07. Pie chart breakdowns compared to the ones Mansi showed you, of course, where I'm really keen on the 1As, but we find lots and lots of other things. Again, this is through 2024. And then if I do the same thing for everything up till now, this is really impressive. And of course, I now sympathize with my advisor because the only way you can build this is by yelling at your students to please help observe all the time. So again, in redshift distribution space, this really does pull you through to get you an anchor sample with Rubin. And again, if I go through all years, especially as we've added DECAM, we can find supernovae out to Rubin redshifts. And so I'm really, really excited about the overlap with Rubin. We've been getting transient and photometric redshifts for many of these things. There are interesting sources where they disagree, and that makes us believe that the Rubin deep imaging will really help. There might be some faint host galaxies for some of these things that we can't see, and we're misassociating hosts for them. And not a huge number, but enough to see. The nice thing about having such good data is you can ask Claude to just make you a plot of 25 of them randomly, and you can pretty much be guaranteed to get something like this because they are all really, really well sampled. They didn't have to do anything. Now, I could do light curve fits to all of them, and you'll see some, but for the most part, you can trace them out with your fingers. Where does Rubin come in? Well, we started observing the same fields, ECDFS and EDFS, during DP1 with Rubin, and we found several of the supernovae that were in both Rubin and our DECAM data, and we pulled out light curves for all of them. The DP1 period is just that those blue vertical regions. So you could see with just the Rubin data from DP1, we wouldn't have even been able to tell you what the light curves were, but because we were co-observing at the same time and forcing the reductions at the same time, we could really pull out the full light curve evolution for all of these sources. And so there's a whole bunch of these things. And the nice thing is, even though the DP1 supernovae already happened and are already on disk, we can replay alerts through them. And we've been building a model at the NSF Simons AI Institute for the Sky, or Sky Institute, called Selden, that actually does real-time forecasting and classification of these as the light curve evolves, complete with reasonable uncertainty quantification, which is really fun. And it turns out this model is only trained on simulated data. We haven't shown it a single bit of real data, but it still works. So, you know, Bansi and Danielle and others are busy trying to get us spectra, and I'm trying to focus on all of the supernovae that we cannot possibly get spectra for. I think we can photometrically classify them pretty darn well. But the nice thing about the sort of model that we're using, these things called foundation AI models, is that they can use more than just the light curves. So luckily for us, Rubin DP1 also overlap with Euclid, free data on the host galaxies. So with Charlotte Ward and Irfan Urbaksh, Charlotte just had to take off. We've been doing this joint pixel processing program that James Colbert and others had us look into. So we have ComCam images as well as Euclid Viz and J images off of these, all of many of the supernovae. That's enabled us to get better redshifts. But more to the point, we can combine all of this to get better host morphologies for the galaxies. And with the same model, take all of the Rubin data on the top right there, combine it with Euclid and build host SED models for every single one of those transients. So we can get things like star formation rate and metallicity for every one of these. And I'm looking forward to industrializing this and doing this over the entire Rubin Euclid overlap region. So it's a very, very powerful, fun tool. And the key here is to try to automate this, which we're doing with agentic AI. We've been working with the Danish IDAC for Rubin to see if we can actually make this happen at scale. I don't know what happened to the title a little bit there, but the next step is, of course, DP2. And as I said, we've been moving our DECAM fields further and further south, so we'll have more and more overlap with Rubin. We know there are supernova in DP2. We just need the PVIs to pull out the photometry. So DM team, as soon as you can, I'll throw more grad students at this and find you more light curves. And I think it's more than just that we will add color information and cadence. Again, we will have host galaxy properties. So this really will be the best defining sample and probably the quickest path to testing whether lambda CDM is the right paradigm or not. And of course, many of you know that the DECAM field of view doesn't match up to Rubin. So we've really been burning DECAM time, tiling the regions as well as you can. So I'm particularly excited about the DECAM tie-ups with the DDFs, where I really think we'll have exquisite light curves. In some cases, with Cosmos, for example, we also have light curves with pan-stars that go back to 2008. So all sorts of interesting lensed objects, quasars, etc. So I'll quickly wrap this up. We have the largest, lowest low-Z GRIZ photometric sample. We've shown that we can tie our calibration of DECAM to Rubin and pan-stars. We can take all of these things and get photo-Zs for them. We can forecast what we can do with an LSST year one sample, which we'll eventually have with DR1, but I intend to do this with DP2. We built the infrastructure to do a joint analysis in paper by my postdoc Ayan Mitra. And we're now finishing how to do the host galaxy connections by combining Rubin and Euclid and DECAM together. And here in the forecast from Ayan was what we think we can do with around just DP2 level data with Rubin in the next couple of years. So we're very, very excited to put all of this together and really answer the key question. Is Lambda right or not? I certainly hope not, but stay tuned.
We have time for questions.
Thanks, Gotham. I know you've walked me through some of this stuff multiple times. On the Rubin Euclid stuff, do I think of your SED as having been generated as a DDP 2 or 3?
Okay, so DDP3 is joint pixel processing with Rubin and Euclid together, which we have done for all of these supernovae. So that was what Charlotte has done. That improves the morphology model. The thing that looks like a blob starts to show some structure. We pull out the photometry from that, and then we had to do a little hacky stuff to get it into this model called Aeon1, which I'm sure you've heard about from Francois Denus and Liam Parkers and other folks around here. And basically treat the LSST photometry like HSC photometry for now, and then that's what gave you the SED inference. So we were able to do this. It's very brittle. It needed some hand holding, but it does work now for all of the 20 some odd transient sources that we have. And it is the sort of thing that, again, will take some work to industrialize, right? But that's the next step.
Any other? If not, let's thank Katim and let's eat.